Everybody. So we're going to continue talking about the graphs of sine and cosine. This is what we were doing in the last video. And so what we had come to was that both sine and cosine were periodic functions with a period of 2 pi. And this is the notion that they repeat, that if you shift by 2 pi, you'll get to the same place, right? And I have graphs up here. Cosine is the graph in blue, sine is the graph in red. And if you notice, if you just keep moving over by from any point to another point, 2 pi different from it in the x direction, and either way, the function's at the same height, the same output, right? So our definition of periodic functions, remember, was something like f of x is equal to f of x plus p. So any periodic function has this fact. When its period is p, as long as you're in the domain of the function, this holds true. So sine and cosine, and we see in this graph, they're both periodic, and they really have the same shape. You can think about the circle, the unit circle definitions of these to realize they're doing the same thing, just starting at different places, maybe is one way to think about it. They're phase shifted. We'll have a little bit of language around what that means later in this video. We also look at their domains. Their domains are all real numbers. This again comes from the unit circle definition, which changes them dramatically from what their domains are when you think of them in terms of triangles. Their range is between -1 and 1 inclusive. And then we talked about cosine is an even function, and sine is an odd function. So those were the big pieces, and we want to get familiar with these graphs that I went through last time. But recall the reason we do any of mathematics is so that it's useful in the world, right? And as scientists, you might find yourself using sines and cosines to help model some little piece of the universe. And seldom does the piece of the universe we want to model match perfectly with these. And so we generalize these a little bit, sines and cosines, or expand on them a little bit, is maybe a better way to say it. And we're going to look at sinusoidal functions. And so what we mean by these, we're going to have 4 constants. We'll call them A, B, C, and D. Are constants. And I want A and B to be non-zero. So both of these, neither of these can be 0, right? C and D can both be 0. And all of them can be anything except A and B both cannot be 0. So I should say neither can be 0. Not that they can't be 0 at the same time. Neither one of them can be 0 at all. And by sinusoidal function, we mean functions of the following form: A sine bx minus c plus d, or y equals a cosine bx minus c plus d. Okay, so first, let's notice why a can't be 0. Is if a is 0, we don't have a sine or a cosine function because it's wiped out by that 0. If b is 0, then our input is always 0 or negative c, meaning this is just a constant function, the value of sine at that. So a, b, and c and d are constants. A and b are not equal to 0. Well, what you might notice, if you recall from previous courses, these are just transformations of functions, what we're doing here. So it's more familiar perhaps to look at something like, if we have the function y equals f of x, we can perform transformations right? This can be done to any function, and these transformations are what we've done to sine and cosine. And you might recall what these transformations do. Let's remind ourselves. We'll go through in detail. I'm going to look just at sine to make this a little easier. So this first the first constant a, if you multiply a function by a constant, you get a vertical stretch or compression. So I can make the dotted line as the original sine function where a is just a 1. And we see we can stretch or compress. If we multiply by a negative, it flips it upside down. We can still stretch and compress it. So that's what a does. Put it back to the original. If you multiply, so b, notice, is multiplying by the input. That gives us a horizontal stretch or compression. In the case of a periodic function, we can also say it changes the period of the function, right? So right here, the function is repeating every 2 pi. If I compress it perhaps to about here, now I'm repeating it every pi, right? So I've made the period half as big. On the other hand, I can also stretch it out. Now I've made the period twice as big. So we can change the period of the function or horizontally compress and stretch this function. There's the original. Then let's look at C. C is we're subtracting inside the function, and this does a horizontal shift, right and left, depending on how much we subtract or add. And then finally D, adding outside the function, gives us a vertical shift. Right. And then, of course, we can combine, we can take combinations of these transformations, right? So we get something that still is familiar to a degree, but obviously is much different than the original function. So we're going to go through each of these in detail, or at least some amount of detail. Some are a bit easier than others to wrap our heads around. Because we want to get familiar with using them. This is how we make the sine or cosine function match the particular piece of the universe we want to study. So let's start with the a value. So if we take y, I'm just going to do it in terms of sine. So we have one picture to look at, but the same things will apply for cosine. And if we transform y equals a sine of x. So we're multiplying the function by a value. It's pretty simple to think this one through. If we, for instance, let's just put in some values. Just do a couple. Let's do 0, pi over 4, and pi over 2. Right? So sine of 0 is 0, sine of pi over 4 is root 2 over 2, and sine of pi over 2 is 1. When we take a sine x, all we're doing is multiplying those outputs by the number a. So the zeros don't change because it doesn't matter what a is, that's still going to be 0. When you multiply root 2 over 2 by a, you're just going to get a root 2 over 2, and 1 becomes a. So if a is a number larger than 1, what have we done? We've made all these outputs bigger. In other words, they're moving up, right? So this point here where the value of the function used to be 1, if we've multiplied it, I've got an a value of 2.1, has now moved up to 2.1, right? And every point has scaled that same way. Oops. Right. Notice, of course, the zeros don't change. The function is still going through all the same zeros on our graph. If a was smaller than 1, we would shrink each point. So here I'm at a point where a is 0.4. So the point that was at 1, the output was 1. Now the output is 0.4. So we get this vertical stretch. And then, of course, if it's negative, so here, for instance, is -1, we've just flipped the whole graph, right? Everything has flipped upside down. So we describe this, or we give a name to this, we will call a, or the absolute value of a, the amplitude, okay? And it's exactly the same as any vertical stretch that you may have learned about for any function in the past, but we do give it a special meaning when we have sinusoidal functions. Notice this value A, so for instance, here I'm at 0.4 again. This max point is at 0.4. This minimum point is at 0.4. This distance here is 0.4. The distance here is 0.4, right? So this amplitude is going to be the, one second, how do I stop this again? Okay. The amplitude is going to be the distance of the max mins to, I want to say 0, right? Notice in my drawing I picked it to 0, but what we want to be a little more general later when we shift our graph up and down, it won't be the distance to 0, it'll be the distance to what we call the midline. Okay, so regardless of how we shift our graph around, whether it's at 0, there's a point or there's a line that's always in the middle of the graph. And this distance is going to be the absolute value of A. So if the absolute value of A is larger than 1, that distance increases from 1. If it's smaller than 1, it decreases. And then if it's positive, our sine graph looks the same as it's going up in the same places that sine is going up and down in the places it's going down. But if we make a negative, it flips it over, right? So the negative determines whether or not we flip it first, and then the size of A, the absolute value of A, determines whether we stretch it or compress it, okay? And so that will be our A value, the amplitude of the function. We'll talk more about the midline in just a bit. Actually, let's jump to that. I feel like I'm pinned into going in the order of A, B, C, D, but there's no good reason for that. So let's jump to that midline. What controls the midline? Well, let's put this back to the original. So A is equal to 1. Let's look at D. D is our vertical shift. Right. And in fact, let's put in the line y equals D. Notice what happens as I change D. That blue line is the horizontal line y equals D. When D is equal to 2, that line's right there. Notice that line is always in the middle. When D is equal to 0, that was our x-axis, but as we shift, that line always splits this graph in half vertically, right? Those little mounds on top are exactly the same size as the little mounds on the bottom. This line is our midline. Okay, so y equals sine of x. We transform to y equals a sine of x plus d. Oops, I'm going to do one at a time, so I'm going to not worry about the a right now, but we'll see how to combine them a little later. Sine of x plus d. And really, you've seen transformations before. We combine them in the same ways that we do there. It's just we're doing them for these particular functions. And so this is our vertical shift. I guess I never wrote this up here. I should say that this a value is a vertical stretch compression, depending on the value, as well as the negative flipping it. Well, this is a vertical shift, right? So if D is positive, it goes up. If D is negative, it goes down. I'll leave it up to you to do a little table like this, but it's very simple to see what happens as you output sine values, then you add a number. And so all the numbers go up by 1 or down by 7 or whatever number you're putting in for the D value. What's really important in particular for sines and cosine is the line y equals D is the midline of the graph, right? And so If we know the amplitude from the A value and the midline from the D value, right, you can draw that midline and you know how far up and how far down it goes. We're changing the range of this function. So originally, if, well, let's look at this dotted line on our graph. That goes between -1 and 1. But as I shift D, the range is changing, right? So let's add some more to this. Here's D plus 1, y equals D minus 1, right? Our range is now in between 1 above D and 1 below D, right? And if we also were to change A and stretch it, we get a similar changing of the range. So all of these will have impacts on the range of the function. Okay, that is our D value. That's that. Let's now jump to the B value. All right, so what does, let's spend a little more time on this one. If we start with y equals sine of x, and we transform to y equals sine of bx, let's see exactly what happens. So let's use the following example. Let's graph a couple points just like before, and look at what happens to the sine of x and the sine of 2x. So I'm taking the value for b to be 2. I'll do the same points I did last time. 0, pi over 4, pi over 2. So here we get sine of 0 is 0, pi over 4, sine of pi over 4, root 2 over 2, sine of pi over 2 is 1. But what happens when we multiply the input by 2 first, right? So, well, when it's 0, nothing changes. We're still 0. If I put in pi over 4, 2 times pi over 4 is pi over 2. The value is 1. And if I put in pi over 2, 2 times pi over 2 is pi. The value of sine of pi is back to 0. So what's happened here? Well, let's just take a quick look. So I'm just going to graph from 0 to pi over 2. Here's our pi over 4 value. The original graph I'll do in red. Sine of 0 is 0. Sine of pi over 4 is root 2 over 2. Sine of pi over 2 is up at 1. So 1's up there, and we get the beginning of that first quarter of our period. However, when we multiply the input by 2, we're starting at 0, but the pi over 4 output is now up to 1. And the pi over 2 output is now down to 0. And we'll get a graph that does this. We've done half of our whole cycle, right? So what does sine usually do? It goes up, back down below, and back up. So in the red graph, we've just begun the going up. We still have to go back down, then we have to go back down and back up. But in the blue graph, we've already gone up and back down, right? We're going through the values more quickly because we're multiplying that input by 2. We're getting our inputs quickly. So we're compressing it horizontally. So let's look at our graph over here. As I change the b value, in this case, I'm making it bigger. So what did I change it to here? 2. We've compressed the whole graph. We've squeezed it in, okay? Values that were far away are now getting closer to the y-axis. If I make it less than 1, we start stretching it out. If we flip below 0, we reverse. It's like flipping it over the y-axis. Because of all the symmetries of sine and cosine, it looks identical to flipping it over the x-axis, but there are some differences, but we can compress it in that way. We typically don't do this, though it will happen on occasion. We'll focus mostly on positive values of b, but they can be anything, so we won't ignore them, but we will focus on positive. And for the positive values between 0 and 1, we get a stretch, right? It's getting, points are being pulled away from the y-axis, and values bigger than 1, it's getting pulled closer to the y-axis, okay? This affects the period. So let's think about the period of sine. So typically the period is 2 pi, right? So if we begin when x equals 0, I'm just going to look at one period. We're going to end when x equals 2 pi. That's the basic sine graph. When you input 0, you get the beginning of the period. At 2 pi, we're finishing that period and starting the next one, right? I could have picked other values. These are two easy ones to pick. Let's look at now let's think about inputting 2x instead of just x, right? So the blue is our original graph. Oh wait, I switched colors. Well, in any event, now let's think about inputting instead. We input 2x. Well, the beginning of our period is going to be when 2x equals 0, right? I'm thinking in terms of input. So in both cases, I'm looking at the beginning when the input is 0. In the first case, it was just x equals 0. Now it's when 2x equals 0, but of course, this is equivalent to x equals 0. And it ends when the input is 2 pi. Originally, that was when x equals 2 pi. Now it's when 2x equals 2 pi. I can solve for x. It's when x equals pi. Let's look at our picture. Let me go back to b equals 2. Notice what happens. By the time we get to pi right here, we've done a full period of sine. We've gone all the way up, back down, back to the middle. Up, down, below, back to the middle, back to the midline, right? In half the amount of time, because we're spitting out the inputs more quickly. That 2 is doubling how fast we go through inputs. So it takes us half as many inputs to get the same number of outputs. That's how I often think about it. So we've cut the period in half here, right? And notice how we found that. I looked at the beginning, it stays at 0, but if the end is now going to be 2x equal to 2 pi, we divided by 2. For any a value I choose, b value I choose, that period is going to be 2 pi divided by whatever number I have here, right? If I had chosen 4x instead, I could do the exact same thing. The 0 is not going to change because it doesn't matter what's sitting here. It still means x has to equal 0. But the period itself is going to be 2 pi divided by whatever number I put there. So what's the takeaway of all this? Well, transformations of sines and cosines are exactly like transformations of any other function. But because of their periodic nature, we will think of, because of a lot of things about them, we think about the transformations a bit differently. It's convenient because of their periodic nature to, instead of thinking about how much we're compressing it or stretching it, to instead think about b as being related to the period. So the period is going to be 2 pi divided by b, okay? And this is the way we'll typically think about this b value, what it does. It determines the period for us. That is the same as saying it stretches or compresses horizontally, but when we're graphing sines or trying to interpret graphs of sines, it's much easier to just look for a period. It's very easy to see how long does it take this thing to go up and down and back up again, right? And so that's going to be the piece, the way we usually frame the value of b, right? So each of these letters has some particular signifier in the graph, right? We started with a. was the distance from the midline, how tall this graph is. D gave us the midline. B is connected to the period by, I keep pointing at my screen, by this formula here. The period is equal to 2 pi over B. Okay, we're almost there. We've got one more to go. Let's look at the C value. Okay, so let's look at y equals sine of x and consider what happens when we transform into y equals sine of x minus c. Okay. The minus in there is not universally written this way. You know, let's, before we even talk about what c means, let's just think what that looks like. If c is a positive number, you'll have x minus, let's say 2. You'll have sine of x minus 2. If c is a negative number, you'll have x minus 2 or x plus 2. So you have to remember that c is going to be the opposite sign of what you actually view in that function, because we've got the negative in there. Okay, so everything I'm doing is in terms of if we're thinking of c as the opposite of what we see there. So let's dig into what that does. Okay, so we'll do a similar graph. I might do one extra value this time, or sorry, table. So I'll get my x. We'll think about sine of x. And we'll think about sine of, I'm going to do c is equal to pi over 4. And see what happens here. Okay. So let's, I did 0. We're going to do pi over 4, pi over 2. Let's do one more. For some reason, I find this one to be a little bit trickier to think about. So we'll do 3 pi over 4. All right, so our familiar values, sine of 0 is 0, sine of pi over 4 is root 2 over 2, sine of pi over 2 is 1, sine of 3 pi over 4 brings us back down to root 2 over 2, okay? All right, so now, and maybe a little unit circle here will help to think this through, or a good way to visualize this, okay? So, sine of 0, of course, we just did was, when we computed sine of 0, we're just thinking about the angle here. What is the x coordinate or the y coordinate of, oops. So this is 1, 0. So when the angle is 0, it's just laying flat and we pop out that 0. But now when we put in 0, we get negative pi over 4. So that's an angle, right? Because I've got this subtraction in here. So when I put x equals 0, my input is 0 minus pi over 4 or negative pi over 4. Well, this point here is going to intersect through the same point we would hit if we were going in the positive direction, right? Root 2 over 2, root 2 over 2. However, the x coordinate doesn't change, but now the y coordinate is in the negative direction. So we're at negative root 2 over 2. So let's put that in. Negative root 2 over 2. When we input pi over 4, we get pi over 4 minus pi over 4 is 0. Sine of 0 is 0. When we get pi over 2, when we input pi over 2 minus pi over 4 is pi over 4. Sine of pi over 4 is root 2 over 2. And when we input 3 pi over 4 minus pi over 4 is pi over 2. It's 2 pi over 4 or pi over 2. We output 1. Let's sketch this really quick. So we're going to go, here's pi over 2, pi over 4, 3 pi over 4. Do the original. We start at 0. By pi over 4, we're at root 2 over 2. By pi over 2, we're up at 1. And by 3 pi over 4, we're back down to root 2 over 2. So we get the beginning of the graph as we start heading back down, right? Of course, it will continue on. This shifted graph, well, we start when the input's 0, we're starting down below at negative root 2 over 2. We're hitting 0 here. By pi over 2, we're at the value root 2 over 2, and by 3 pi over 4, we're at the value 1. So something like this, and if we had continued going, we'd see it would go on and on and on. So what has happened? This point that was at 0 has moved forward. This point that was at pi over 4 has moved here. We're getting this horizontal shift, right? If I had drawn in more of the original sine graph, we'd see a point over here shifting forward, okay? So that, if you remember your transformations, when we when we add or subtract inside the function, we get a horizontal shift to our graph. So let's look at that on here. So I need b equals 1. Here's the original. Let's do some shifting around by changing the c value, and I can move this sine graph backwards and forwards. I've only set it to maximize at pi, but you can do any amount of shifting you want, right? And one thing that you might notice, you might already be seeing, is here's the graph of cosine. This is something I had mentioned earlier, that they really have the same shape. They're just shifted a little bit. If I shift the right, oops, I need to go this way. If I shift the right amount, that sine graph is now sitting on top of the cosine graph, right? They're doing the same thing. They're just starting at different positions, okay? And this is what we call the phase shift, okay? How far are you moved from the original position, right? So I usually think about it in terms of, with sine, how far has that 0 point moved is a good way to visualize it, right? They're all going to move the same amount, but it's nice to have a point to anchor to, okay? So this c value is connected to the horizontal position, okay, or what we'll call the phase shift. How far has it moved? So if we connect it to the, let's look at this one I just did, sine of x minus pi over 4. This is our function. One way to think about it is, like I said, what happens to the 0 point? In other words, sine of 0 is at 0, so I want to know what endpoint gives me a 0. So for instance, if I did x, I want to know when is the input equal to 0, because that will give me an output of 0, and that tells me where I can anchor my function. So in this case, it's x minus pi over 4 is equal to 0. It tells me x equals pi over 4. So that 0 point that's normally, the output 0 is normally at input 0 right here. We've moved it to x equals pi over 4, and that's our new output of 0 beginning point, okay? So at first glance, it seems like the c value is what we're going to call the phase shift. My c was pi over 4. I phase shifted pi over 4. However, let's think more generally. When we combine these transformations, let's play the same game. If I have a function bx minus c as my input, the question is, when is bx minus c equal to 0? Because wherever that 0 point is, that will tell me how far I've moved. Well, just solving this equation, adding c to both sides, dividing by b. This will actually be the phase shift. It's not c alone. We have to consider what b is doing to it. And it's somewhat clear to see why, because b value is stretching horizontally, and then we have this horizontal phase shift. That stretching also changes where that shift happens, and this is how they are related, okay? One thing to be careful, sometimes people will write, you can, actually I don't need to make a new line, let's just do it right here. I can factor b out of bx minus c to get this, right? So with a little bit of algebra, you can see that that's the same thing. So depending on how it's written, the phase shift is either going to be, if we have a coefficient of x and the c by itself, then we take c divided by the coefficient of x. If that's already been done, if it's already been factored out, then the number sitting right here will be the phase shift. In either case, we'll talk about the phase shift is c over b, okay? This is how far to the right or left our graph moves. If this is positive, it's going to move right. If it's negative, it's going to move left. So let's do one quick example with this factoring. If I had something like 2x minus pi, well, here I could use the phase shift as c over b, which is going to be pi over 2. Or if somebody decided to factor this, it would look like this. And we see now that the pi over 2 is just the number sitting there. So if it comes to you in factored form, you can either expand it to make it more familiar, or you can just recognize that that number in there is going to be the phase shift. Okay, we'll do some examples in another video. This one's getting long. Let me just finish by summarizing what we have. We're looking at these sinusoidal functions. Y equals a cosine bx minus c plus d. And we've come to the following conclusions. A is the amplitude, which is the distance to of the max and mins. Let's write this. Let's just say it this way: maximum distance of graph from midline, right? So in either direction, up or down, what's the furthest away the graph gets, okay? Y equals d is the midline. The period is 2 pi over b. The phase shift is c over b. Okay, so these are all the transformations we can do, and this is what they do to them. It's exactly the same as when you learned about transformations of any function. We just have some extra, ultimately more convenient ways to think about them, and some slightly different vocabulary around them, to help us understand these pictures of these graphs and what these values will do. And this is how we transform our functions to match the little piece of the universe that we're most interested in studying. One last thing I'll say, this can get confusing and it takes a little while to get used to these. There's never any shame in just plugging in some values and plotting some points, right? It is a perfect way to learn what these do. Absolutely, when you're starting to experiment with these graphs and you see something like y equals 2 sine of 3x minus 4, try to think about what that might do to the graph and maybe even make a quick sketch. But certainly when you're done with that, in the beginning when you're learning these, plug in some points and just see if they match, right? Anybody can put in a value for x, compute it, use a calculator, multiply by whatever a is, add d, and see what the output is, and see if that graph, if that point lands on the graph that you sketched. And that will go a long way into helping us understand why these things do what it is they do. Okay, that'll be it for this one. Thanks, everybody. I will see you next time.